Okay, so from the previous example, we can determine the gradient vector, which based on the function given, and at the same time we can also determine by using the gradient vector that we obtain. We also can determine the normal vector to the surface given. Okay, normal to the surface given. All right. Okay, with the condition that the function given should be then equal to constant, where you have to transform the surface to be a level curves. Then you can obtain the normal to that level curve. Okay. So the continuation of this property, which is the normal gradient, is the normal to the level curve. So we look at the next is we can say that using the gradient vector, we can also determine the normal vector to any surface given. Okay, from the previous result, it is shown that we can determine the normal vector to the level curves, where you have to make it the z here to be constant, and you from the surface you have a curve or level curve, right? So now the extension to that, we can say that the normal vector, we can use the gradient to determine the normal vector to a surface. Okay, what is the meaning of normal vector to a surface? Okay, let's say you are given a surface. Okay, let's say you have a flat surface. So now imagine you have a flat surface, which is I give you a plane. Okay, and this plane we have a flat surface. So the normal meaning that your on at any point on the plane, okay, let's say you choose one point, and the tangent line of them, the tangent line of each of the point, they are always the same, right? So there is a tangent line, there is another tangent line, there is another tangent line, there is another tangent line. So the normal, as we know that the normal vector is always perpendicular to the tangent vector. So if, let's say, so I choose one tangent, that is a tangent, let's say that is a tangent at the point here. So the normal vector to this plane or this surface is in this direction. Okay, so let's say I choose another point here where the what we call that, the tangent line, maybe this way. Okay, that is a tangent line at the point here, so the normal vector or the unit normal vector will always the same. So that is the end, and they have always the same direction of end, right? So the end always the same when your surface is flat. But if your surface is something curvy like this, okay, so your end, your normal vector to the surface always change, depends on the point that you have. So let's say you choose a point over here, so you have a point here. So at that point you have a tangent line, right? You have a tangent line, or you can say that you have a tangent plane, okay, where it is parallel to this line. So we have a tangent plane. So the normal vector to this tangent plane is in this way. So if you have a point over here, so your normal vector will be that way. If you have a point here, so normal vector will be that way. So that is your end, and that is your end. Or I can write down like this. So these are all the unit, the normal vector to the surface for any points lying on the surface, which is not a flat surface. So I will say that For a non-flat surface, the normal vector is different depending on the point P where the normal vector is located. So that is the idea of the normal vector to a surface. Okay. So then you can evaluate the normal vector whether you have a capital N or small n, they will be the same. So as we know that the normal vector that we have calculated just now, normal vector to the level curve or the normal vector to a tangent plane or tangent line is given by the gradient f, right? But then if you have you divided the gradient f by its magnitude, then you have a unit normal vector. So to answer this one, how can we compute the normal vector to a surface? So normal vector to a surface, in this case, if you are dealing with the unit normal vector, so in this case, let's say we are using capital N or small n. So the gradient divided by its magnitude, as I mentioned earlier just now. So that's it. That is only the formula to obtain the unit normal to the surface. Okay, unit normal to a surface. Where is your surface comes from? Your surface is coming from the scalar function given to, because the scalar function is, if it is in terms of xy, z is a function of xy, you must have a surface, right? Then we can use this, the gradient of this function, then you can evaluate the unit normal vector to the surface. Okay. All right. So now look at the question here. Find the unit normal. So unit normal vector of the surface given at the point at the specific point 1, 0, -1. Okay, so if you're asking me, as I mentioned earlier just now, is your capital N here is the same as the capital N that you obtained from capital T? Yes, it is the same, but the way you calculate them is different because you have a different information provided. So if you have the unit normal vector, which is from the unit tangent, so you have the information about the vector function. You are given the r, right, and then you have to evaluate r prime, and from there you have to evaluate the t. So that is the telling you the vector function of the curve in space, or the vector function of the curve in 2D system. Okay, but for the topic that we discuss now, unit normal to the surface, you are given a surface, so you don't need to obtain the vector function for the surface given. Okay, you just use the given scalar function, and then you just obtain the gradient, and you can get the unit normal vector directly. Okay, but the way you are describing the unit normal from the T and the unit normal that you get from the scalar field here, they are the same. Okay, but the process and the information provided is different. Hopefully you understand that. Okay. Okay, so to answer this question, okay, so to answer the question, the first thing that you have to do is you have to make sure that the function here, whatever scalar function given to you, you must make it equal to 0. Okay, so how can you make it equal to 0? So you have to so to answer A, so answering A, so you just bring everything into the left or everything to the right. Okay, so now you have x, okay, to answer A, x ey plus y cubed minus z squared. So now your function is in terms of x, y, z. Okay, so now you define your new form is the implicit function. So I should rewrite. Okay, so your new function now becomes 3 variable where you have x e y plus y cubed minus z squared equal to 0. Okay, so you have now your function is equal to constant. Okay, equal to constant. So in this case it is 0. Okay, so what I want to say here, for any function given to you, you have to make it equal to 0. Okay, so next you have to, because we want to obtain find the unit normal, so n is gradient f over its magnitude. So we have to obtain the fx, fy, and fz. So for fx, you have e y, that's it, right? And then for the second component, you have to differentiate with respect to y. So you have x e y plus 3y squared. And then the z component, this one 0, this one 0, and you have minus 2z divided by its magnitude. So you have e 2y plus x e y plus 3y square plus 4z square. Okay, and since the value is given at the point of 1, 0, minus 1, then you can obtain the normal vector at the point given is, so you just substitute the x is equal to 1 and the y equal to 0 and the z is minus 1. Okay, so now without obtaining the vector function, you just use the information about the scalar function given, but you have to make it equal to 0 first, and then you just obtain the gradient f and its magnitude and substitute the value for the point given, and then now you obtain that unit normal vector is as this. Okay, you can directly obtain the unit vector. And let's say they ask you to sketch this, but I'm sure that it is quite complicated to be sketched by hand. So you can see that this vector at this point will always normal to the surface given, which is this one. Okay, the surface of this. Okay, so now look at the, okay, let's try look at the C first, because this one you have to look at the question, but I don't have the question at the moment. So just look at the second question here. Okay, so the same procedure, you are given a surface. What is this actually? So this one is actually hemisphere, right? How do I know that this one hemisphere? So you can rearrange. The equation becomes x squared plus x squared plus y squared equal to 14. Then you have a sphere with radius square root 14, but because of your z here is always positive, then you have only hemisphere. Okay, you have the hemisphere because your z is always positive. So the radius is square root 14, and this one also square root 14, and this one also square root 14. Okay, so that is what surface looks like. But then you have to find the normal vector, unit normal vector at negative 1, 3. So x negative. So somewhere at the back. Somewhere at the back here. Okay, because the x is negative. So you have to find the normal to that surface. So obviously without computing, so we can expect that the normal to the surface should be always in that direction at the point given. So that is the point. So the point is at where is the point? Okay, the point is -1, 3, 2. Okay, now you have to obtain this using gradient f over its magnitude. Okay, so then using the function given, so first you have to make it equal to 0 first, and then determine the fx, fy, and fz, and evaluate at this point and divided by its magnitude. Okay, so that is the thing that we want to compute now. So to answer the question C, so we have z equal to square root of 14 minus x squared minus y squared. So then you have to rewrite your function to be equal to 0. So you have z minus square root of 14 minus x squared minus y squared equal to 0. So you have to compute the gradient f, which means that fx, fy, fz. Okay, differentiate partially with respect to x. So this one will be 0, right? So you have -1 over 2, 14 minus x squared minus y squared to the power of -half and multiplied by -2x. So okay, this one is only computing the fx first. Okay, I want to compute the fx first. Okay, so this one is only fx. And when I simplify that, then we will get x over square root of 14 minus x squared minus y squared. Okay, and I'm sure for fy we will also get the same, but this one becomes y square root of 14 minus x squared minus y squared. And then fz we only get 1. So now we put into the gradient f, so we obtain that x over square root 14 minus x squared minus y squared, and y over square root of 14 minus x squared minus y squared, and then 1. Okay, so then we evaluate the grade f at this point given, which is at the point -1, 3, 2. -1, 3, 2, yeah. Okay, so then when we evaluate that, then we will get -1. So 14 minus 1 minus 9. So we will get 4, square root 4, right? So we have 2 in this one, 3 over 2, and 1. Okay, so that is our grade f. But since we want to obtain the unit normal vector, to gradient f over its magnitude, then -1 over 2, 3 over 2, 1 divided by the square root of 1 over 4 plus 9 over 4 plus 1. So we have 10 over 4 plus 1. So we have 14 over 4. Is that correct? Ten over 4. And so 14 over 4. Then we have a square root there. So then we have 7 over 2. Okay, we have the square root of negative 1 over 2, 3 over 2, 1 divided by 7 over 2. Square root of 7 over 2. Right? Okay. And then when we simplify that, okay, so that is the unit normal that we obtain. So I put in the 4 decimal places. Okay, so now if you look at the result here, so we managed to compute the unit normal to this hemisphere, where the answer here is given like in this. Okay, and if they ask you to sketch that, and of course the answer will be there, which that arrow is coming from the summation. How can you get the value somewhere over here? Is the summation of the point that you have here and the point of your initial point, which is negative 1, 3, 2, and you will get this error. Okay, so that is the example. Okay, there is another way. How can, okay, maybe you might wonder, how can we see that the because on the previous video I show you the gradient f is always perpendicular to the level curve, right? But then how can suddenly we can show that the gradient f is always perpendicular to the surface f itself, right? So this is the surface f, and the gradient f is always perpendicular to the surface f. So how can we obtain that or prove that? So for that, I want to show you here how can we show that the grad phi, so let's say your scalar function is phi, is always perpendicular to the function, the scalar function phi. So in this case, to show the gradient phi always perpendicular to the surface phi, okay, which means that this symbol saying that the gradient phi is orthogonal, perpendicular to the surface phi. Okay, so in order to show this, actually we can use the previous proving, which is we are using we show that on the previous lesson I have show you that, just a second. Okay, I'm using to show that I'm using the level curve, right? And the level curves. So we have shown that the level curve, so the gradient f is always perpendicular to the level curve here, right? Or I would say that always normal to the level curve. But in this case, the level curve here is actually lying on the surface itself, So then we can say that instead of we say that the gradient f is perpendicular to the level curve, so we can also say that the gradient f is perpendicular to the surface f, because of we know that the level curve here is also the level curve. So you can see the level curve here, this line is also on the surface. Okay, but in a proper way, here I show you again how we can say that the gradient f or the gradient phi is always perpendicular to the surface phi. So so we have a vector function. So the vector function in general given by x, y, z. So what is this? So this is a vector function of the level curve, right? Just now we obtained that when we put z equal to any constant, so we have a level curve. So we can obtain the vector function of that level curve. So it's given by RT. So I just, sorry, okay. So I just put the R. And it is understood that we have RT here, and X is in terms of T, Y in terms of T, and Z is in terms of T. So R here is the vector function of the level curve. And we know that the level curve is part of the surface phi. Okay, when you assume that the phi or the f is equal to constant, so from the surface you can have a level curve. Okay, the thing that I show you from the previous video. So we have R vector function. So from R we can obtain the tangent vector, which is dr dt, right? Dr. So which means that when you have dr, you have dx, you have dy, and you have dz. Okay, so now you are given a scalar function phi, whatever equation that you have, and as from the previous example, I give you two examples from this. Before this, we always make sure that the function is always equal to 0 or constant. Okay, so 0 or constant. So as we done before, we always make it equal to 0, or we can just say in general we have a constant. So the scalar function given is now rewrite into a constant or 0. Okay, remember last on the previous example, we have z equal to square root and so on, and you just bring the make it equal to 0, so you have z minus square root whatever in there is equal to 0. So that is phi actually, or f. Okay, so now when you differentiate the phi, and because it is constant, so the answer is 0. So the phi here can be rewrite into in a derivative form. So in order to get the d phi, so you can or del phi, so you can have del so maybe del phi del x to dx plus, and you will get the del x and dx cancel out, right? Okay, it's just a symbol. Okay, and then still you, or you can the other component del phi del y dy, okay, plus del phi del z dz. Okay, so because of this one is always equal to 0, so you also have 0 here, because when you simplify this, you will get this tag. Okay, del phi is equal to 0 because this is constant. So now from there, this one is actually the dot product between, so del x, del phi, del y, del phi, del z, dot with the dx, dy, dz, where it is a gradient phi dot dr. So gradient phi, we know that gradient phi, from phi we just evaluate, find the vector gradient phi. And what is dr? Dr is a tangent vector. Okay, tangent to the level curves, and the level curves is actually part of the surface, lying on the surface of phi. So since dr, okay, dr that we have, which is a tangent vector, right, to the level curve, is also on the surface phi. So we can say that now, because of the answer here is 0, right? Because we have this one equal to 0. From the beginning, we set equal to 0. Because when phi is constant, when you differentiate, so you will get 0. So this one of all of them will be 0, and this one is actually from the dot product between the gradient phi and the dr. So because of the dot product between them is 0, we can say that the gradient phi and the tangent vector is perpendicular. And since the tangent vector is also lying on the plane on the, remember that from the previous video I show you that at z equal to 9, so you have a level curve, so your z is you have a plane z equal to 9, right? So the tangent vector here is always on the plane z equal to 9, for example. So the dr here is actually also part of the surface. So since the gradient phi is perpendicular to the tangent vector, so we can say that so here we can see that the gradient phi is perpendicular to the tangent vector. Therefore, gradient phi also perpendicular to the surface phi, because of the dr here. Why? Kenapa kita boleh kata sebab dia perpendicular dengan terhadap dr, and tiba-tiba you ada phi sebab dr ini adalah juga dalam surface tersebut. Okay, selari dengan surface tersebut. So then kita boleh kata gradient phi also perpendicular to the surface phi. Where actually you can see that from the previous video that I show you the this one. Okay, this one you can see that where is your, just a second, you can see from here. So this is your level curves. So level curves is part of the surface, and your tangent here, your tangent is in green color. Okay, and then the gradient also and the gradient is given by the red one. Okay, so this is from our previous video, which is you say that the gradient f is always perpendicular to the level curve. So that we can say that the gradient f also perpendicular to the surface, or instead of we say perpendicular, so we say normal. So the gradient f also perpendicular to the surface, or we can say the gradient f is normal to the surface. Okay, normal to the surface. So how can you say that the gradient f is perpendicular to the f? Okay, so your f is hyperbolic. So this is hyperbolic. So just now you obtain that when the z is equal to 9. Okay, so somewhere over here, right, this one. So you choose any point on the surface. So you choose any point on the surface, let's say over here. And we already obtained from the previous video, when you calculate the r and the tangent vector of this level curve, we obtain that the gradient phi, okay, is point or normal to this surface, which is where you obtain that from this calculation, from this sketching. Okay, so because of this one is part of the, you can't see in 3D because this one is just sketched in the curve, but this one is actually part of the part of the surface. Imagine there is a surface here, and you can see that the gradient f here is always perpendicular to the surface f. Surface f, which is this one. Surface f. Perpendicular. So because of, we can sketch the tangent line. So the tangent line is here. So that is a tangent. Let's say that is a r prime or t, and this is your n. So then we can say that using gradient, we can obtain the normal vector or unit normal vector to the surface. Because you can't see that clearly because this one in 3D is quite complicated to see directly. Okay.